today we'll continue talking about the chapter 4, which is about the pressure, subsurface pressure, and the fluid dynamics. So the section 3 and section 4 will talk about pressure and the phase of the hydrocarbon. So subsurface pressure can be measured in many ways. You can measure it during drilling and after drilling and before where it's drilled. And generally we know that the velocity increases with depth as sediment compacts because you have a decrease in porosity, and reversal of the velocity trend may indicate the under-compacted and hence overpressure shale. So overpressurization. Sometimes in theory, you should have a pressure increase with depth linearly, which is what? The function of the density of water, right? But some formation you have instead of this, you have an increase in pressure, and you have a higher pressure than the hydrostatic pressure. So this is the overpressure zone or overpressurized zone, and this is normally caused by the unconsolidation of the weakly consolidated soil. So let me give you an example. You have a deposition. For example, this is the water, and this is fish. You have a deposition of the layers, and when the soil or sediment is deposited here, and you have another layer coming in, right? And another coming in, and another coming in. So then this layer will have increasing pressure or the overburden stress, so that the water should escape because there's overburden stress increasing. But what if this overburden layer is very low permeability layer? Like this is the clay layer or shale, so that the water cannot escape. This is called the undercompaction or unconsolidation. So that the fluid here is being pressed, but there's no path the fluid can escape. Right? So you have a high pressure region in here, and then the pressure will increase like this. So this is so then, because it's not fully compacted, the sediment itself will have a low strength, and the porosity will be high because it's not fully compacted. It's called the overpressurized zone. And when a well is being drilled, a number of parameters may indicate the abnormal pressure. So the first one is the rapid increase in rate of penetration. So during the drilling through the overpressure zone, so as drill bit going down, when you meet the overpressurized zone, that the porosity is very low, high porosity, right, because it's weak, and so that the penetration is easy relatively. But because it's overpressurized, as you drill the hole, it's like you are drilling a hole at the balloon, right? The fluid will just come out. So there's a risk that you may have kick out. So that rapid increase in temperature of the drilling mud. We're going to talk about this one soon. And density the decrease in density of the shale cutting. So in the under-compacted zone, as you cut through with the bit, you have a rock chip coming out that will have the low density than the other depths. So let's look at the example here. So this is the velocity. So this is the PV velocity. So as depth increases, as you go deeper, as you go down, it's normal, it is absolutely general that you have increase in velocity. But in this boxed area, the red box area, you have sudden decrease in velocity. There's a reversal of the trend. And what is here? Mud flow line, the temperature of the mud. This is the temperature in the borehole during the drilling. And you have a rapid increase in temperature. Why? So during drilling, you have heat generated, but because the rock chip cut by this drill will have the low density, so the thermal conductivity also very low. So low thermal conductivity. So it doesn't release the heat very efficiently, less efficiently. So you release the heat less efficiently so that you have a temperature increase. And penetration rate, of course, you have an increase in penetration rate because it's a weak formation, so that it's easier to cut it. And shale density also have a low shale density. And resistivity itself, you have very low resistivity. I think this is because of the high porosity. Too high porosity. High porosity. Okay. And for the overpressure, so to detect the overpressurization, people use this D exponent, which is, I think, the abbreviation of the drilling exponent. And this drilling exponent is function of R and the N. So R is the rate of penetration, N is the rotary speed, so it's RPM, and the W is the rate of pit, and D is the diameter of borehole. So as you go deeper, because the porosity will decrease and the formation itself will have a higher density, so the exponent will increase linearly as you go deeper. So that means that if you keep the rotary speed, the rotation of the bead constant, and the weight of bead will be the same, and the diameter of the borehole will be the same, then the rate of penetration decreases with the depth. But when you reach the top of the abnormal pressure, at which the depth, this D exponent will be reversal, so it will be increasing. So rate of penetration increases at the overpressurized zone, abnormal pressure zone. Okay. So, and there's always a issue with the kick problem. So you have a gushing of the fluid coming out of the drilling well because of this overpressure. So then it is very important to detect the overpressure zone before you hit that zone, or when you hit the top of that zone, so that you can increase the mud weight, or you can do some remedy to prevent the gushing. So once the well has been safely drilled, then pressure can be measured by several methods. Okay. So for question, 질문 혹시 여기까지 up to this point? No? There are two types of pressure. Actually, this is not the pressure. This is stress, overburden stress, and there's a lithostatic stress, or some people call it lithostatic pressure, and there's a fluid pressure. And lithostatic pressure is the same with the effective stress. This is the same concept with the effective stress that we have in soil mechanics. And fluid pressure can be hydrostatic when there is no flow. This is the no flow. And there is a hydrodynamic fluid pressure, and there's fluid flow. Right? If the fluid moves, then you have a different pressure. Right? So there's a CPG component, and this is a with flow. And lithostatic pressure or lithostatic stress is the same with the effective stress, which is caused by the rock mass transmitted through the grain-to-grain contact. And lithostatic stress gradient varies according to depth, density of the overburden, and extent to which grain-to-grain contact may be supported by the overpressure. So but there is an equation for the correlation among these three components. And we know that the overburden pressure, this is the same with the total pressure. Or sorry, total stress. And lithostatic stress is the effective stress. And the fluid, the pore pressure component. So the overburden pressure is equal to the summation of lithostatic pressure plus fluid pressure. So this is basically the same with the sigma equals sigma prime plus u. So here the sigma prime is the effective stress, and the total stress is the sigma, and the fluid pressure is u. So in geotech or the soil mechanics, we use this symbol, and here they use the different symbol in the geology. The concept remains same. So if the fluid pressure increases, which means that this U component increases for a given overburden stress, then this will decrease, right? This lithostatic pressure will decrease. So at some point, if this one increases too much, then you have a plastic behavior and this effective stress goes to zero, so you have a quick condition and failure in the sediment. Right? So this is the same. The effect may transform the sediment into an unstable plastic state. This is failure. That means the failure. What else? Okay. So can we measure the pressure, fluid pressure? Yes, right? We can measure the fluid pressure using piezometer or pressure transducers, right? What about the overburden pressure? Can we actually measure or estimate it? I think theoretically we can measure it if you have a very large plate. Right? But the people usually estimate and calculate the overburden stress by what? By the density. Right? You have a density profile, then you multiply the depth and the gravitation acceleration, you can get the overburden pressure. And the lithostatic pressure, which is effective stress, this is unmeasurable. You cannot measure it. Very difficult to measure it. So people only can calculate from these two factors. So this is kind of a conceptual value, but which is very important in the mechanics. Okay. So how can we calculate the pressure then? I think that this is too obvious. So this is the gradient for the overburden pressure, or overburden stress, and this is the gradient for the pore pressure, or the hydrostatic pressure. So I think this book uses the FIT and the PSI, but we can convert it to the SI unit, scientific standard unit. So the pressure, water pressure is what? Water density time, gravitation time, the depth, right? And overburden stress is also total density times G times G, right? So 1 feet is equal to 0.305 meter, and the 1 psi is the same with the 6.895 kilopascal. So then 1 psi per feet. So here 1 psi per feet is the this gradient how much is it in meter, kilopascal per meter? So can you calculate it? Please give me the number. You can divide this 6.895 by 0.305. And what do you have? 22.6 kilopascal per meter, right? Then, well, this gradient assumes the rock density, right? Then what will be the value of the rock density this gradient assuming? 22.6 kilopascal per meter. You can divide this value with the gravitation, right? So 9.8, and they will give you the density, the bulk density of the rock. How much is it? No. 2.3. So that I think this gradient assumes that the rock density of 2,300 kilogram per cubic meter. Right? And we can do the same calculation for the hydrostatic pressure. So it's been described as psi per feet, but if you convert it, it becomes the 10.3 kilopascal per meter, and then it assumes that this water density. So actually considers the salinity of the water. I think this assumes the salinity of 88,000 ppm. Again, if it's just 0 ppm, then this fluid density will be 1,000, right? 1,000 kilogram per cubic meter. Okay, so then we talked about how we can calculate the hydrostatic pressure. So this is the when there's no movement of the water. Right? And then what if we have the water movement? Then hydrodynamic pressure gradient of the fluid potential gradient, which is caused by the fluid flow, and piezometric level, we can measure the piezometric level. And this is defined as the level to which the fluid would rise if the well were open. Then, for example, in this diagram, you have water intake at the mountain area, and you have a groundwater discharging to the valley area. Right? So there should be a water movement from here to here. Then what you can do is that you can drill a well, drill a hole, and just install a pipe. Then there will be a water coming up. Right? I think that this will go around to here. And then you can measure the depth of the water surface from the surface. Then you will find out the total energy or total head of the water at each point. And that total head tells you the energy of the water. So always the water flow from higher energy to the lower energy, right? Or the higher elevation to the lower elevation. And so here you have, I think this is going that direction, right? From here to this point, there is a low total head, the high total head, so this will go this direction. And you can find out the pressure. This is the same idea what we did in the soil mechanics or the fluid dynamics. Total head is the same with the elevation head plus pressure head. Right? And there is also the velocity head term, but we ignore this is almost zero. In geologic condition because the water flow will be very slow. And you can if we look at the total head here, total head is this much, and if this datum, and the velocity head will be 0. Oh, no, sorry, the elevation head will be 0, so we can calculate the pressure head, vice versa. So either way, we can identify each head and the elevation, each head, elevation head and the total head and pressure head. From there, we can calculate the flow rate from one direction to the other, and one point to the other, and also the flow velocity. Okay, and the potentiometric or the piezometric level is horizontal, which means that this is almost horizontal, like this. Then there's no flow because the energy difference is there's no energy difference, so energy level will be the same. But if the potentiometric surface is tilted, then fluid is moving across the basin in the direction of the dip of the surface, and the fluid pressure is caused by the hydrostatic and the hydrodynamic forces, which is the CPG component. I think we've done this a lot. Let's look at this equation first. So fluid potential is the total energy of the water, so level to which formation fluid rise or fall to attain the potentiometric surface. And you have a two term here. What is this? P over density. This is term of, is this the pressure head term or elevation head term? 윤수는 토리력하게 들었습니까? 나한테? It's been a while, but is this the pressure head or elevation head? So here the large P is fluid pressure. Oh, thank you. This is a pressure head. Actually times G. And this one is G, this is the gravitation acceleration, 9.8. And Z is the datum elevation, so this is the elevation head. So fluid potential is defined as the head times the G, gravitation acceleration. And here the head is the total head. Okay, so then there's a pressure gradient you can calculate from the groundwater surface, or groundwater surface, right? And it will increase with respect to depth and the density. And if the pressure is the same with the hydrostatic pressure, it's called the normal pressure. If the pressure is less than the hydrostatic pressure, it's called the subnormal. And it's more than the hydrostatic pressure, it's a supernormal pressure. We'll talk about it in next few slides. Okay. Then, what if we have a oil reservoir, right, in the channel? So this is the sandstone formation, and you have a water flow at all the time, and you have a trapped oil in here. And if you find this inclination, C over D, then the inclination will be proportional to this potentiometric surface inclination. So H over D and times the density difference here. So slope of the oil-water contact is related to the fluid potential and also the density difference. And this tilted oil-water contact is caused by the hydrodynamic fluid flow, because you have a water flow coming in and going to this direction. Yeah. If there's a static, then the contact should be horizontal. because it's not static, you have a tilted angle. Can we move on? Okay. Within any formation with an open pore system, pressure will increase linearly with depth. This is hydrostatic. When separate pressure gradients are encountered in a well, it indicates that there's a permeability barrier which separates the formation. So, for example, you measure the pressure at certain interval. Here you have a measurement, so that increases, and suddenly you have a drop in pressure and start again. So then you have a one gradient and you have the other gradient in shallow depth, and this means that this region you have some impermeable barrier which separates the two geology formations. Okay, we're gonna talk about the supernormal pressure and the subnormal pressure very briefly. Supernormal pressure, the pressure that is greater than the hydrostatic pressure, and they are found in sediment ranging in age from Cambrian to recent, but especially common in tertiary deltaic deposit, such as the North Sea, Niger Delta, and Gulf Coast of Texas. And study of the causes and distribution of overpressure is very important because overpressure presents a hazard to drilling and is closely related to the genesis and distribution of the petroleum. Why? So overpressure, the presence of the overpressure zone means that there is a permeable barrier. Then you have a high chance to have a trap so that the oil can accumulate. So finding this overpressure zone is positive in terms of the petroleum exploration, but it may have a negative effect in terms of the drilling. So overpressure zone occurs in close pore fluid environment, and where fluid pressure cannot be transmitted through permeable beds to the surface. Two aspects are nature of the fluid barrier and region for the pressure buildup. Permeable barrier inhibits the pressure release, maybe lithological or structural. Common lithological barrier are the evaporite and the shale. So this is the salt dome. And the shale can be a cap rock, lithological barrier. And the less common are the impermeable carbonate or sandstone. A cap of the carbonate cemented shale often occurs immediately above the overpressure interval. Structural permeability barriers may be provided by fault. I think we're going to talk about this one later in the chapter 7. More. Chapter 7. So the major causes of the overpressure, first the artisan and structural, compactional, and diagenetic. And we'll talk about briefly. So structural cause is a block of sediment can be raised between two sealing faults, and compression of the strata giving fold can cause overpressure. So I think you have a deposition, and maybe this is the permeable layer, and you have a cap rock, and tectonic force comes, and you have a compression, so that you have an overpressure zone here. And you can have some sealing fault too. And compactional cause is the one that I told you just before. So commonly in muddy delta where deposition is too fast, for sediments to compact and dewater is in the normal way. So that So the sedimentation was too fast and the water didn't escape, couldn't escape, so that you have overpressure left over. And mineralogical reaction during diagenesis can cause overpressure, like the dehydration of the gypsum to anhydrate and water, and volcanic ash to clay and carbon dioxide, and also the mormolionite. It can give the free water and the water of the crystallization. So overpressure shale have lower densities because it's undercompacted, and the lower thermal conductivities than the normally pressurized shale. It's a unique feature. That's the characteristic of the overpressure shale. Okay. So example of the supernormal pressure. So say that look at here, this section, then sand and the clay are commonly interbedded. So you have a sand formation in the clay, and you have a decrease in porosity, yes, and in the clay region, you have a certain increase in porosity, and the pressure also, you have a increasing pressure in the clay region. Or the shale region. So porosity remain high, and the pore pressure exceeds the hydrostatic pressure. Subnormal pressure is straightforward. It's the pressure less than the hydrostatic pressure. Subnormal pressure, you have a naturally, so it only occurs in a reservoir that is separate from the circulating groundwater by a permeable barrier. So you should have also the permeability barrier that disconnects the fluid flow or the pressure communication. And the naturally occurring subnormal pressures are found in both structural and stratigraphic traps, and subnormal pressure may be caused by three main processes: increase in pore volume and decrease in reservoir temperature, and the production of the petroleum from a sealed reservoir. So increase in pore volume means that you have a compacted sediment, and by some reason, if there's extension or the volume expansion, then inside the pore pressure will drop. Right? So that's the decompression or fracturing. And the decreasing reservoir temperature is by cooling, so that reservoir cools and the fluid pressure will go down. And the production of the petroleum means that you are sucking out some fluid in the reservoir, so that the pressure, fluid pressure will also decrease. And there is no aquifer to allow water to flow in to replace the produced petroleum. So example here is that first one, this structure is all connected to the groundwater, right? So that the fluid inside this permeable bed will be hydrostatic. But here, this is not connected to the top, right? This can be disconnected. Also, it doesn't have the pressure communication between this formation and this formation. So this can be a normal or the overpressurized zone. And here, also it's an isolated zone, so it could be a subnormal or the supernormal pressurized zone. And if you take out and produce the hydrocarbon from here, then the pressure will decrease suddenly, and there will be no replacement because it's fairly isolated. So this is just a conceptual drawing about how the subnormal and the supernormal pressure can be developed. Subnormal pressure in a confined system or increasing pore volume causes pressure drop. So this is very obvious. And the erosion of the rock above a normally pressurized reservoir will cause a decreasing of overburden pressure and hence an expansion of the rock. So you go back, like here, if you have an erosion by this much, then overburden pressure will decrease so that you have a decompression, so that the pressure will decrease. So it tells you about the pore volume also increases. And I didn't tell you the scale here, but this scale could be 100 kilometers. Right? So from here to here could be like Seoul to Daejeon or Seoul to Busan. Right? So just imagine it, that's very large scale here. We are not talking about the kilometer or the 100 meter. It's 100 kilometer scale. Okay. Any questions so far? 여기까지 질문. 그래서 if we talk about the basin scale and the geologic formation, whether it has the hydrocarbon or not, it's about the scale of Ulung Basin or like the West Sea Basin, like 100 kilometers, hundreds of kilometers, right? Could be 1,000 kilometers. It's a very large basin we're talking about now. Okay, I think this is easy. So pressure, we talked about the temperature and pressure, right? And pressure and temperature affects the fluid characteristic. Right? If it's too hot, then this component, some component will present as a gas, and some component will present as liquid, depending on the pressure and temperature. And also, is when you produce it from the subsurface will have the high temperature and the high pressure. And when you produce it, you cool it down and the pressure will be released. So then suddenly you have a volume increase. The hydrocarbon will expand a lot. And also you have an exsolution of the gas coming out of the hydrocarbon. So that chemical engineering very concerned about this phase change and phase transformation in the hydrocarbon. So they always look at what will be the phase boundary of the methanol or the like paraffinic oil or the aromatic oils, and that's what they do. And the pressure, the gas bubble will nucleate from the liquid, and from here, if you cross this phase boundary, you have a gas coming out, so gas bubble nucleation. So that if the pressure decreases, the gas will come, and if the temperature increases, then you have a gas bubble nucleation, right? And it's called evaporation, 증발. And the opposite reaction is the condensation from gas to liquid. So you have temperature decrease, this direction, the gas will be condensated. And if the pressure increases, also the liquid will be condensated. Then a pure fluid may exist in either the liquid or gaseous state, depending on the pressure and temperature. But subsurface fluids are a mixture of the many components. Then bubble point and dew point. The finding out the bubble point and the dew point for the mixture is also one of the research topics in the chemical engineering. So this is the case. You have two components. Two component mixture. So if you have the single phase or the single component, like for example water, what is this? Ice and the liquid water, and this is the vapor. Right? And this line tells you the phase boundary that there's a coexistence between of the liquid and vapor, right? And here, along this line, you can have the ice and the liquid water together, right? Because you have a line, because it's a single component. When you have a two component, then you have an area pressure and temperature regime that can have the liquid and the vapor together. So from here to here, you have evaporation. From here to here, you have a condensation. And in this region, you have a phase equilibrium between liquid and vapor together. So then, this phase equilibrium will vary depending on the molecular weight of your hydrocarbon and the viscosity of your hydrocarbon. So from light oil to heavy oil, from here to here is a low molecular weight and it's a heavy molecular weight. The phase diagram will shift like this. So here's the liquid region and the vapor region. And the amount of the gas that can be dissolved in oil increases with pressure, therefore the depth. And the lower the density, higher the API gravity, the more dissolved gas it contains. And within a reservoir with separate oil and gas column, the two zones are thermodynamic equilibrium. Okay. So then, let's do this. Okay. We'll talk about, okay. So far, any question? 여기까지. 혹시 질문? 다른 건 없어요? We have secondary migration of the petroleum. So when there's a source rock where the hydrocarbon is generated, you have a primary migration from the source rock to the permeable carrier bed. And then the secondary migration is the movement of the hydrocarbon through the carrier bed to the reservoir. So let's say that we have this kind of a formation. And in deep depths, you have a source rock where the hydrocarbon is generated. And then this hydrocarbon will somehow have to move to the carrier bed. This is called the carrier bed, which is generally the permeable formation. Maybe it could be a carbonate or sandstone. Then because of the buoyancy, because the hydrocarbon is lighter than the water, so that this will migrate and they can be trapped in here, right? If there's a cap rock here, maybe salt dome or shale. And this is called a trap. And from here to here, it's called a secondary migration. From source rock to the permeable bed is called the primary migration. And to move this oil droplet through the water, it is two-phase flow. So you have a sandstone full of water, and there's a droplet of the oil that's moving inside this saturated sandstone. So the capillary pressure between the oil and the water becomes important. So that further movement can only occur when the displacement pressure of the oil exceeds the capillary pressure of the pore. We'll talk about it soon. And this is the Young-Laplace equation, which calculates the capillary pressure. I think this is the same that we learned from the capillary tube experiment. So for example, I think we did this experiment in the physics or the solid mechanics class. We have let's say that we have a very thin tube, and you plug that thin tube in the water, then the water will rise, right? Water will rise to a certain height. And this height is proportional to the capillary pressure. And the tension, surface tension, is the interfacial tension here, this I. Or some people use the gamma or I. Okay. What is the surface tension between water and air? How much is it? Okay. 0.08, 0.7, 0.72 Newton per meter at 20 degrees. This is the surface tension between water and air. And you can have different value, but still you have a surface tension between water and oil, and that affects the capillary pressure. Okay. So as the oil droplet build up beneath the narrow pore throat, however, they increase the pressure at the throat until a droplet is squeezed through the opening. This process will stop when the sediment pores are so small that the pressure of the column of the oil beneath is insufficiently to force further movement. The oil has become trapped beneath the rock. Okay. So let's look at this figure. This figure shows that let's imagine that you have soil compaction. Compacted sand like this, and it's fully saturated with water. And you are injecting air bubble, or it could be oil, doesn't matter, like immiscible fluid, anything. Right? Here is full of water, and air is coming in, and maybe air gets trapped in here, right, before they permeate through because of the capillarity. Because sand has very small pore, so then capillary, the pressure of the air and the pressure of the air should exceed the capillary pressure and the hydrostatic pressure that's here. So the air wants to come in and invade like this, but it has to exceed some value, which is called the capillary pressure. So the air pressure and capillary pressure plus the water pressure here, they are competing each other. Right? So if you increase the air pressure, and if you keep increasing it, at some point, this air pressure will become larger than this two value, right? The TC and the PW. Then you start invading. So what if you don't have the soil? If you don't have the soil, then you have air coming in, then air can just flow in if the air pressure is just larger than the water pressure at the bottom here. Right? Does it make sense? Because there's no trap or there's no pores. As soon as you have a pores like this, then the pore size affects your capillary pressure, and capillary pressure will act as a barrier to blocking the air. And that happens to the oil too. So this diagram shows that when the oil is invading this direction, the pore size D will block the oil droplet invading more, so that you have to calculate this capillary pressure 4 times T cosine theta over D pore, or I think this becomes the same with this previous equation. If you convert it to the radius R, and this is the D. And if the oil pressure minus water pressure is larger than the capillary pressure, you can invade. So then, if this D is much small, initially the capillary pressure can be larger than this oil and this pressure difference, oil pressure minus water pressure. And then there will be more oil coming in. Droplet will migrate and then it can accumulate to a certain depth or a certain height. And then what happens? The buoyancy force will increase. Right? Buoyancy force is what? Force becomes the, how do you calculate it? The weight of the fluid replaced by this oil, right? That's the buoyancy force. So then buoyancy pressure is the force divided by the area. So weight of the displaced volume, the water volume, divided by the area will give you the buoyancy pressure. So then this accumulated oil height can be used to calculate the buoyancy pressure. So then as the bubble, the oil bubble is coming up, then you have increase in H so that the buoyancy pressure will keep increasing. So at some point that this oil can invade through the soil, through the sediment or through the rock or through the shale. And this process will stop when the sediment pores are so small and the oil has become trapped beneath the cap rock. And this is called a fine-grained cap rock by capillary pressure, and it's called the capillary seal. Capillary sealing or capillary trapping. So for those who is interested in the geology carbon sequestration, this is the same. When you inject the CO2 carbon dioxide can be trapped by this capillary seal. So you have to find the proper sealing formation, like shale or with a very low pore size. Then you can store the carbon dioxide safely. Otherwise, it can invade because you keep injecting the CO2, so now the pressure of the CO2 will increase. Then this equation is basically the same. The depth, this is the height of the oil column. And Y is the interfacial tension. And R is the throat, the radius of the pore in the cap rock, and G and the, so this is comparison between the capillary pressure and the buoyancy pressure. Buoyancy pressure. And then you can derive this equation. So what this graph telling you? As the grain size decreases, which means that the pore size decreases to this direction, pore size R decreases, right? And then the height of the oil accumulation also increases. So then, what do we need this equation? Why do we need to calculate this height of oil column? To predict the amount of the oil in reservoir. So this is related to the how much the trap can store the oil by this capillary sealing. Capillary sealing is likely to become be more effective for oil than for more mobile gases. Gas entrapment, so capillary sealing is more effective in liquid hydrocarbon than the natural gas. Gas entrapment may be due to pressure seals, where the pressure due to the buoyancy of the hydrocarbon is less than the excess pressure of the shale or above hydrostatic. And pressure seals are common where the overpressurized clay overlie normally pressurized sand. The pressure gradient is locally reversed from the usual downward increase to a downward decrease. And once oil or gas has reached an impermeable seal, be it capillary or pressure, it will move horizontally and displacing water from the pore. So once they reach this capillary sealing, then they cannot intrude vertically, so they they will spread laterally. And this lateral displacement can be like up to 400 kilometer, like from like 100 kilometer. It's the order of 100 kilometer. After this is the summary. I can just read this through. Summary of the chapter 4. Familiarity with the subsurface environment is necessary in order to understand the generation and migration of oil. And rock density, temperature, salinity, pressure increases with depth where the porosity decreases. The local reversal of these trends occurs in intervals of the overpressure zone. Hydrologic regime of a basin evolves with time from use to seniority. A young basin has a very dynamic fluid system, but deep conic fluid movement declines with age. So immediately after deposition, overburden pressure causes extensive upward movement of the water due to compaction. This movement is commonly associated with the migration and entrapment of hydrocarbon. Upward fluid movement may be locally interrupted by zones of overpressure. So this is explaining about the compaction causing the upward fluid movement. And as time passes, the basin matures, hydrocarbon generation ceases, and overpressure bleeds off to the surface, and pressures become universally hydrostatic and subnormal because of cooling and erosion. In some presently normally pressured basin, the presence of the fibrous calcite along veins and fracture may be a relic indicator of the past overpressure. Okay. Meteoric circulation will continue in the shallow superficial sedimentary cover. Deep conic water may continue to move, albeit very slowly, in convection cell. This hypothesis is the best example. So in the young basin, this is the comparison between young basin and the old basin. And young basin, here you have a meteoric water coming in and the circulation, and hydrocarbon and conic water migrate from basin center. So hydrocarbon will move and they can be trapped at here, right? And old basin, meteoric water circulates in shallow rock and degrades the oil and possible slow deep conic water convection cell. So you have a low fluid dynamics, less fluid dynamics compared to the young basin. I think that this is the young basin case. You have a pressure increase, overpressure due to compaction. And in the old basin, because of this overpressure has been bleed off, it's been released, so that instead you have a subnormal pressure because of the erosion. So there are big differences between the young and the old basins.